All right, guys, welcome back. We've got lecture video number 3 here for chapter 16. Finishing up chapter 16 today. I'm putting this one in the books here. I'm going to kind of just clean up some things, talk about the different types of electrochemical cells that we mentioned in the last video. Starting out here with our very first one known as our voltaic cell, guys, aka a battery, right? A voltaic cell is quite literally a battery. It's not really any other way to think about it. A voltaic cell is a battery, and a battery is a voltaic cell. They're very, very interchangeable with each other. If you call something a battery, you're also calling something a voltaic cell. If you're calling something a voltaic cell, you're also calling it a battery. Now, again, guys, batteries don't just produce electricity out of thin air, right? Or a current, essentially, out of thin air, right? Or electrical energy. Although it is spontaneous, that doesn't mean it just comes out of thin air and comes from nothing, right? What it actually comes from is chemical energy, right? Chemical energy, it's a chemical reaction occurring that produces this idea of a voltage, of electrical energy. So it just doesn't happen out of thin air. When we're producing electrical energy out of nothing, right? We produce it from chemicals essentially mixing together to produce this current, to produce this spontaneous redox reaction that essentially creates electrical energy for us, right? And again, oxidation occurs at the anode with that anox representation, and reduction occurs at the cathode with that red cat representation, right? That other mnemonic device we talked about last class, right? Now, it's important also to recognize that electricity is going to always flow from the anode, which is going to be negatively charged, to the cathode, which is going to be positively charged, right? So keep that in mind as we start to sort some differences between our different types of cells here, right? So this is, again, everything for a voltaic cell here, where electricity flows from the anode to the cathode. That's not going to change. It's always going to be from anode to the cathode. But what will change here, guys, and you'll see this shortly here, is the charge of the anode and the charge of the cathode. Again, for voltaic cells and batteries, the anode is the negatively charged side and the cathode is the positively charged side. So, but keep your eye on it, on the charge of the cathode and the anode when we compare this to our electrolytic cells here. Now, electrochemical cells, or these electrolytic cells are electrochemical cells that convert electrical energy into chemical energy. Now, you might be thinking to yourselves, and I mentioned this, in the last video, as well as in class with you guys, right? What would be the point? What feels like would be the point in converting and turning electrical energy into chemical energy, right? Why do we care about being able to create and make a chemical reaction occur that wouldn't normally occur unless it had some kind of outside energy source, right? That's the whole point here, right? We essentially are taking batteries here, right? And if I take a battery out of my my calculator, right? What would be the point of taking a battery, for example, using the electrical energy that this thing creates from its chemical reaction, wiring this up to something to then being able to charge and create a chemical reaction that would not have normally occurred, right? What would be the point of that? Well, that's going to kind of be what we talk about today here, right? Being able to discern why we would even think about wanting to use batteries and electrical energy to create and make a chemical reaction occur that would not have normally already occurred, right? That's going to be part of our discussion today here. But again, the key thing here with electrolytic cells, guys, is that they require a power source, right? Like just like a battery would be a great example, right? To drive the chemical reaction to actually occur. Now, oxidation still does occur at the anode, right? So anox still occurs here, and reduction still occurs at the cathode, right? Red cat here, right? REDCAT, red cat. Electrons still do flow from the anode to the cathode, but again, the big change here, guys, is the charge on the anode and the charge on the cathode. Notice how the charge on the anode this time is a positive charge, and the charge on the cathode this time is a negative charge, right? So this time around, instead of electrons flowing from the anode to the cathode, that's positive or negative to positive, this time around we're flowing from the positive to the negative, right? So anode was negative here, cathode was positive here, so it was from the negative terminal to the positive terminal. This time around here, guys, it's the exact opposite, right? It's still anode to cathode, however, it's going to be from the positive side to the negative side for our electrolytic cells. Now, some example of electrolytic processes here, guys. This is going to be a great example of why these electrolytic cells are actually useful to us, right? They undergo what's known as a process called electrolysis. And this idea of electrolysis can be used in so many different ways and so many different applications in the real world here. With a process called electroplating, which is quite literally, guys, a process in which a metal is coated with a very, very thin layer of another metal, such as silver, for example, right? So if you guys, wear any chains or have any earrings or something like that, right? A lot of times, some of the more cheaper things, right, are not going to be 100% gold or 100% silver, right? They're going to be plated in gold or plated in silver, and this is exactly the type of process that is used to do that thing, right? So to plate our earrings and our chains in gold or plate them in silver, right? They undergo a process called electroplating, which is exactly what an electrolytic cell helps achieve, right? So for example, thinking about like the term silverware, right? If you guys ever are eating your dinner, right, or your lunch, breakfast, whatever, with a fork or a spoon or a knife, whatever, right? Yeah, they're more generally called cutlery, but sometimes people will refer to them as silverware. Now the idea of them being silver is basing this hundreds and hundreds of years ago, right? So forks and knives and whatnot, for especially people that were more well off and were richer and whatnot, quite literally did use forks and knives and spoons that were made out of silver, right? But they weren't just straight up made out of silver; they were actually plated in silver, right? A very, very thin coating of silver was applied to these metals like iron and aluminum, for example, right? And sometimes even steel. Steel is the more widely used one these days, right? Oftentimes, if you look at a lot of your silverware these days that's in your kitchen, you're going to see things like stainless steel, right? Stainless steel is going to be a popular one these days, right? It's cheaper and more durable than silver is, right? But again, years ago, when people had the money, they would use silverware, right? That was literally made out of silver. But again, it underwent a process known as electroplating by applying a very, very thin layer of silver on the outside of your forks and your knives and your spoons, to kind of make them look really, really nicely and nice and silver. Okay. But again, this idea of electroplating is behind so many different things like silverware, silver, gold-plated jewelry, all that good stuff. So what happens is they basically will take a battery like we see here, right? This battery is in this example, is a 9-volt battery, and they'll hook up 2 little probes to it, right? And the one probe will run to the anode, which is a metal bar of silver here. The other is going to be a probe that gets hooked up to the thing you want to electroplate. So the reaction that ends up occurring here, guys, is that we are basically going to be mixing this with a solution of silver. So this is Ag plus and NO3 minus. So the reaction here is between silver metal, which is going to be your anode, and it's going to be between this reaction of silver solution, which is going to be silver nitrate, right? AgNO3 is going to be our silver nitrate here. So what ends up happening here, guys, is a current runs from this cathode, from this anode to the cathode. And when it does that, essentially over time, is all the silver that comes from this little silver bar here, the silver bar here will essentially scrub away. See these little bubbles reacting? Well, all these little bubbles are going to create Ag plus ions. They're going to then latch onto this particular fork here. And it's going to quite literally plate it in silver, right? So it's a pretty cool process. We get to see that the silver bar here will react in the solution, the nitrate solution we've got here, and it's going to create these Ag ions here. And these Ag ions are going to be becoming essentially, once again, silver metal, by latching themselves back onto another substance, another metal this time around being this fork here, right? So they're going to essentially transfer from this this electrode here, this silver electrode, transfer as a silver element to an ion, breaking down, and then be reattaching itself as another element of silver onto this fork here. It's a pretty cool process, and it's very, very applicable in lots of different fields and whatnot, okay? Now, what are some other electrolysis applications here? Another example of this is known as the hydrolysis of water, right? Which is a fancy way of saying the breaking down of water into its two pieces, right? Hydrogen and oxygen. Is also known as the electrolysis of molten NaCl, right? Which is known as Down's cell, which actually is able to break it down into sodium and chlorine, right? So NaCl is a pretty widely abundant substance, right? But unfortunately, sodium and chlorine, respectively, separately as their elements, are not nearly as abundant. So in order to help do that, we take something super, super abundant like NaCl, we run a current through it in a very, very, interesting way here, using what's known as Down's cell here. We run a current through it like a battery, a voltage source, and we essentially separate the Na from the Cl, producing solid metal, sodium, as well as chlorine gas, Cl gas here, right? This is the whole setup here on the right-hand side. And this is the reaction here, right? We take NaCl, 2 moles of it with a coefficient of 2 here, 2 moles of NaCl to produce 2 moles of sodium and chlorine gas, Cl2 gas right here. Now, what's the point, right? Why would we want to isolate chlorine gas and isolate sodium metal, for example, right? So, for example, sodium metal is used as a coolant in nuclear reactors, right? So, nuclear reactors are another important type of energy source that are used, clean energy source that is used not as widely spread, but you know, it's a pretty important type of clean energy. And in order to cool down these nuclear reactors, because these nuclear reactors, guys, they produce a ton of heat here. In order to cool them down properly, you're going to actually use a metal like sodium to help do that. And of course, thinking of the different types of applications of chlorine, for example, right? Chlorine is it's a wonderful source of water purifying. And it's also used in different types of manufacturing as well. So lots of different applications and uses for undergoing this idea of electrolysis to break apart NaCl into its two pieces, Na and Cl, separately. Now, I'm going to take a minute or two here to kind of break down the differences between our electrolytic and our voltaic cells here, guys. Going through a giant table, sort of asking the question on the left-hand side here as we go down and being able to fill out each side as either voltaic or electrolytic here, right? So the question to start here is, does it require a battery, yes or no? And guys, as we know, voltaic cells themselves are batteries, so no, they do not require a battery. Whereas electrolytic cells are non-spontaneous, so because of that reason, they do in fact require a battery. Next question is the type of reaction. Is this spontaneous or non-spontaneous? And again, your answer here is going to be yes, this is a spontaneous reaction for voltaic cells because they occur without having any outside energy source required, right? Now, on the flip side here, electrolytic cells do in fact require an outside energy source, just like a voltaic cell or just like a battery. So therefore, yes, these are going to be non-spontaneous cells here. Next up here, the site of oxidation is still going to be the anode, right? Remember, anox, right? An for anode, OX for oxidation, anox. Is going to still be the case for our electrolytic cells. Same with our site of reduction here. It's going to be cathode for both of these as well. Now, where do the electrons flow from, in fact? So it's going to still be the same thing for both these guys. They're going to flow from the anode to the cathode in both types of cells, both our voltaic and our electrolytic cells. Now, the problem here is really the difference, rather not the problem. The difference between the voltaic and electrolytic cells we've got here, guys, is the sign of the anode and the sign of the cathode. It's going to be different for both of them. So for a voltaic cell, the sign on the anode is negative, whereas the side on the anode for the electrolytic cell is going to be positive. And then, of course, this ends up flipping on its head for our cathode here, right? So for voltaic cells, the sign of the cathode is going to be positive, whereas for electrolytic cells, they're in fact going to be negative, okay? And that is going to be our nice little concise table. It's going to be a great little resource for you guys to help study, just study up on the differences between voltaic and electrolytic cells for this chapter here, right? Lastly, here is our concept on spontaneity. We don't really want to spend too much time on this idea of spontaneity because what we're going to actually end up doing is taking a really nice look at another piece of a reference table that is this guy right here, right? Activity series, which is called our table J here in our reference table, right? So table J is a pretty great one. What allows us to do is determine if a reaction is going to happen spontaneously or not, right? So table J is used to determine if a reaction is spontaneous or not. Now, how do we use table J? It's very, very, very easy. We'll do a couple examples of this when I see you guys in class next. But how to use table J? Again, very, very simple. For a reaction to occur, the element that is a reactant must be higher on table J than the element that is a product. So basically, guys, what you end up seeing here is that if we look at my little tools are gone. I was trying to find my little drawing tool, but I can't find the drawing tool. That's okay. But basically, for example, if you've got iron metal here, and then you've got something reacting with, let's say, something as basic as copper, for example, right? Because copper is lower, it's not going to react properly with the iron, so therefore it's going to end up being a non-spontaneous reaction. Again, we'll do some examples of this in class here. It's going to make way more sense. But again, table J is going to be one of our last pieces of our puzzle here for our, all of our new material here. And with this end of this video here, that is the end of chapter 16 already, guys. So I will see you in class. Thanks for watching.